Welcome to the chapter on work, energy, power, and collisions. These concepts form a single connected framework in physics. Energy is a property that a body possesses, work is how a force transfers that energy, and power is the rate of that transfer. Collisions are events where energy and momentum instantly redistribute between bodies. In this chapter, you will learn the precise definition of work and why the angle between force and displacement determines its sign. We will cover kinetic, potential, and mechanical energy, along with the true meaning of conservative forces. We will also explore the work-energy theorem as the bridge from forces to energy, discover why power equals force.velocity, and analyze elastic and inelastic collisions using the coefficient of restitution. The underlying through-line for this journey is simple. Force leads to work, work transfers energy, energy is conserved, and conservation governs collisions. Let us begin. A force does work on a body when the body actually moves. It must move in the direction of that force, or against it. If you push a wall, there is no work. This is because there is no displacement. If you push a box across a floor, you do positive work. The force and displacement are roughly aligned. But friction on that sliding box does negative work. The friction force opposes the displacement. Let us look at the formal definition. For a constant force F and a displacement S, work W equals F dot S. This expands to F times S times cosine theta. Here, theta is the smaller angle between the force vector and the displacement vector. Work is a scalar quantity. Its unit is the joule. 1 joule equals 10 to the power of 7 ergs. Its dimensions are m times L squared times t to the negative 2. This is the exact same dimension as every form of energy. The sign of the work depends entirely on the angle theta. Let us read the table. When the angle is 0 degrees, cosine theta is positive 1. The work is positive F times S. The force is perfectly aligned with the motion. When the angle is acute, meaning less than 90 degrees, cosine theta is positive. The work is positive. This means energy flows into the body. When the angle is exactly 90 degrees, cosine theta is 0. The work is 0. There is no energy transfer. When the angle is obtuse or greater than 90 degrees, the work is negative. Energy flows out of the body. When the angle is exactly 180 degrees, the work is negative F times S. The force opposes the motion exactly. Notice there are only two ways to get zero work. Either the displacement is zero, like holding a heavy suitcase still, or the angle is 90 degrees, like the normal force on a sliding block, or gravity acting on a satellite in a circular orbit. The main takeaway is this: positive work transfers energy in, negative work transfers energy out. What if the force is not constant? We handle a variable force by splitting the path into tiny pieces. We call each infinitesimal piece ds. We then add up all the dot products along the path. Work equals the integral of F dot ds. Geometrically, this integral represents an area. It is the signed area under the force displacement graph. Look at the graph on the slide. The work done from point I to point B is the shaded area under the curve. Now consider path independence. For a constant force, the work depends only on the starting and ending positions. It does not depend on the specific path taken. This path independence is the defining property of conservative forces. Friction is the standard counterexample. The work done by friction grows as the path length increases. It is not conservative. As a quick limit check, imagine the force is constant. The area under the graph becomes a simple rectangle. The area is F times S. This recovers our original formula for constant force. Here are three special cases of work worth memorizing. First is gravity. For a mass m rising through a vertical height h, the work done against gravity is m times g times h. Notice this only depends on height. It is path independent. This is a strong hint that gravity is a conservative force. Second is a spring. For a spring with constant k and displacement x from its natural length, the work done by the spring is negative 1/2 times k times x squared. It is negative because the spring force always opposes the displacement of its free end. But the energy stored in the spring is positive 1/2 times k times x squared. Third is a couple or torque. For a torque tau and an angular displacement theta, the work is tau times theta. This is the rotational analog of force times distance. A good rule of thumb is this: the total work done by multiple forces equals the work of their net resultant force. In any state of equilibrium, the net work is always zero. Let us review the key takeaways for work. The definition of work is F dot S, or F times S times cosine theta. It is a scalar measured in joules. The sign of work is decided by the angle. Acute angles give positive work. Obtuse angles give negative work. Perpendicular forces give zero work. Path independence marks a force as conservative. Friction is the main exception. Three formulas carry most problems. M times G times H for gravity. Negative 1/2 times K times X squared for a spring, and tau times theta for a couple. For a variable force, work is the integral of F dot ds. This equals the signed area under the force displacement curve. This brings us to our bridge to the next topic. Work is the transfer of energy. Next, we will look at energy itself. We will study the energy that a body possesses. Energy is defined as the capacity to do work. It is a scalar quantity. It is measured in the same units as work, which are joules in the standard system. It also carries the same dimensions. M times L squared times T to the negative 2. Remember the distinction. Work is the transfer of energy. Energy is the possession that gets transferred. There are many forms of energy. Mechanical energy includes kinetic and potential energy. This will be the focus of this deck. Heat is disordered molecular motion. It is related to internal energy. Chemical energy is stored in molecular bonds. Electrical energy involves current, charging, and discharging. Nuclear energy is the binding energy of the nucleus. Light and sound are forms of radiated or propagating energy. Every single one of these forms obeys the same conservation law. They are freely convertible into one another. Mechanical energy is associated with motion and configuration. Total mechanical energy, EMAC, equals K plus U. Here, K is kinetic energy representing motion, and U is potential energy representing configuration. For systems acted on only by conservative forces, mechanical energy stays constant. Friction or other non-conservative forces break this rule. They convert mechanical energy into heat. Let us look closer at kinetic energy. This is the energy a body possesses by virtue of its motion. K equals 1/2 times m times v squared. This can also be written as p squared over 2 times m. Here, p equals m times v, which is linear momentum. Use 1/2 mv squared when speeds are known directly. Use p squared over 2m when momentum is the known quantity. Note that kinetic energy must always be greater than or equal to 0. There is no such thing as negative kinetic energy. Potential energy is defined only for conservative forces. For a conservative force in one dimension, potential energy U as a function of x is defined by a derivative. The force F of x equals the negative derivative of U with respect to x. If we integrate from an initial position xi to a final position xf, the integral of force with respect to x equals ui minus uf. There are two defining properties here. First, potential energy exists only for conservative forces. Friction has no potential energy. Second, only the change in potential energy is physically meaningful. The 0 point of potential energy is arbitrary. The source highlights three main types of potential energy. First is gravitational potential energy. U sub g equals m times g times h. This applies to a raised mass near the surface of the Earth. Second is elastic or spring potential energy. U sub s equals 1/2 times k times x squared. This applies to springs and elastic media. Third is electric potential energy. U sub E equals 1 over 4 pi epsilon 0 times Q1 times Q2 over R. This applies to two-point charges in a vacuum. The constant 1 over 4 pi epsilon 0 is 9.0 times 10 to the power of 9. Its units are Newton meters squared per Coulomb squared. For a spring, the potential energy is 1/2 times k times x squared. This creates a parabola when plotted against displacement x. Look at the graph. It is an upward parabola passing through the origin. The minimum is at x equals 0. This natural length is the equilibrium position. The curve is symmetric. You get the same potential energy for a stretch of positive x and a compression of negative x. Notice the quadratic growth. Doubling the displacement quadruples the stored energy. Let us recap the sign convention. The energy stored in the spring is positive 1/2 times k times x squared. But the work done by the spring on whatever stretches it is negative 1/2 times k times x squared. The spring force always opposes the displacement. For a conservative force, equilibrium means the net force is 0. This happens when the first derivative of potential energy with respect to x is 0. The second derivative decides what kind of equilibrium we have. Let us look at the three types. First is stable equilibrium. The second derivative is greater than 0. The curve is concave up. If you make a small displacement, a restoring force pushes back toward the center. Think of a marble resting at the bottom of a bowl. Second is unstable equilibrium. The second derivative is less than 0. The curve is concave down. A small displacement creates a force that amplifies the motion. Think of a pencil balanced perfectly on its tip. Third is neutral equilibrium. The second derivative is exactly zero. The object is indifferent, sitting anywhere on a flat segment. Think of a ball resting on a level table. The reading rule is simple. Stable means a minimum of potential energy. This means positive curvature and a restoring force. Potential energy is frame-dependent. This is a subtle but important point that the source flags explicitly. Imagine two observers moving at different speeds. They will agree on the change in potential energy for any given process. But they will generally disagree on the absolute numerical value of potential energy at a given moment. This is harmless in mechanics. Why? Because only the change in potential energy enters our physical laws. For example, in the conservation of mechanical energy, only differences matter. The choice of reference height for gravitational potential energy is the simplest example. Any horizontal plane can be chosen as h equals 0. The trap to avoid is treating potential energy as an absolute quantity. Never do this. Always work with differences, or ensure you have a clearly stated reference frame. Let us review the key takeaways for energy. Energy is the capacity to do work. It shares the same dimensions and units as work. Mechanical energy is the sum of kinetic and potential energy. It is conserved only when forces are conservative. Kinetic energy is 1/2 mv squared or p squared over 2m. It is always positive or zero. Potential energy is defined only for conservative forces. The force equals the negative derivative of potential energy with respect to displacement. Only the change in potential energy matters. Equilibrium is decided by the curvature of the potential energy graph. A positive second derivative is stable, a negative second derivative is unstable, a zero second derivative is neutral. This brings us to our bridge for the next deck. Energy is conserved when nothing external acts. Next, we will connect energy back to forces. We will do this through the work-energy theorem. Let us introduce the work-energy theorem. The theorem states that the work done by a force in displacing a body equals the change in that body's kinetic energy. Mathematically, net work W equals the integral of F dot ds from velocity v1 to v2. This equals 1/2 mv2 squared minus 1/2 mv1 squared. This is final kinetic energy Kf minus initial kinetic energy Ki. We call this delta K. Let us read the signs carefully. If the net work is greater than 0, the final kinetic energy is greater than the initial. Kinetic energy increases. If the net work is less than 0, the final kinetic energy is less than the initial. Kinetic energy decreases. If the net work is exactly 0, the speed remains unchanged in magnitude. This theorem also works in non-inertial frames. You just include the pseudo-force as one of the active forces. Then the work done by all forces, including the pseudo-force, equals the change in kinetic energy in that frame. The work-energy theorem works for any force, constant or variable, conservative or not. It is the fundamental bridge from Newton's laws to energy conservation. Now we turn to the principle of conservation of energy. Energy can neither be created nor destroyed. It can only be transferred from one form to another. The sum of all initial energies equals a constant. This is the most general statement possible. It applies to mechanical, thermal, chemical, electrical, nuclear, and radiant energy alike. Mechanical energy is a special case. The sum of kinetic energy K and potential energy U is constant only when all forces are conservative. Friction, drag, and other non-conservative forces will break this specific mechanical balance. But they never break the full energy balance. The missing mechanical energy simply reappears as heat. The deeper bedrock of all this is Einstein's mass-energy equivalence. Energy E equals delta m times c squared. Here, c is the speed of light in a vacuum. Classical mechanics usually ignores this equation. This is because the change in mass is too small to matter at everyday scales. Power is the rate of doing work. It tells us how fast energy is transferred. Power P equals work divided by time. For a constant force F acting on a body with velocity v, we can rewrite this. Power equals the dot product of force and velocity. This expands to F times v times cosine theta. Here, theta is the smaller angle between the force vector and the velocity vector. How should we read this physically? Power delivered equals the force dotted with the instantaneous velocity. For example, a cyclist produces surprisingly high power on a steep hill, even at low speed. The force required is very large. Power is a scalar quantity. The standard unit is the watt, which equals 1 joule per second. Its dimensions are m times l squared times t to the negative 3. Let us look at the units of power and a common trap. The base unit is the watt, which is 1 joule per second. Engineering often uses the kilowatt, which is 1,000 watts. Mechanical and automotive fields use horsepower. 1 horsepower equals 746 watts. Finally, we have the kilowatt hour. This is where the trap lies. Electrical billing uses the kilowatt hour. It looks like a power unit, but the letter H is in there. Multiplying power by time gives energy, not power. 1 kilowatt hour equals 1 kilowatt times 3600 seconds. This yields 3.6 times 10 to the power of 6 joules. It is a unit of energy. Another trap to avoid involves zero power. If power is zero, it does not mean the force is zero. Consider a satellite in a circular orbit. Gravity is the only force acting, but it pulls exactly perpendicular to the velocity. The angle is 90 degrees, so cosine theta is 0. The power delivered by gravity is 0, but the force is definitely not 0. Let us review the key takeaways for the theorem and power. The work-energy theorem states that net work equals the change in kinetic energy. The sign of the work and the sign of the kinetic energy change will always match. The conservation of energy is universal. Every single form respects it. Mechanical energy is a special case, valid only when all forces are conservative. Mass energy equivalence is the deepest bedrock, with E equals delta m times c squared. Power is the rate of doing work. The dot product form, power equals F dot V, is the most important one to remember. For units, remember that 1 horsepower is 746 watts. And 1 kilowatt hour is a unit of energy, equal to 3.6 million joules. This brings us to our final bridge. The theorem and the conservation law describe a single body. Collisions describe two bodies. In a collision, momentum always survives, but kinetic energy may not. Let us frame the concept of collisions. A collision is a short-duration interaction between two or more bodies. During this time, they exert strong forces on one another. Physical contact is not strictly required. Coulomb repulsion between charged particles is a textbook example of a collision without contact. There are two conservation laws at work here. First, linear momentum. This is always conserved in the absence of external forces. Second, total energy. Energy is always conserved in total, but the kinetic part may or may not be. Why does momentum survive when kinetic energy might not? The strong impulsive forces during a collision are internal to the system. Internal forces cannot change the total momentum. However, friction or internal deformation can drain kinetic energy. They turn it into heat, sound, or permanent structural changes. There are two main types of collisions. In an elastic collision, both momentum and kinetic energy are conserved. In an inelastic collision, momentum is conserved, but kinetic energy is not. The coefficient of restitution is a key parameter for collisions. It is defined as a ratio. It is the relative velocity of separation after the collision divided by the relative velocity of approach before the collision. The symbol is E. E equals V2 minus V1 all over U1 minus U2. Here U1 and U2 are the pre-collision speeds. V1 and V2 are the post-collision speeds. These speeds must be signed along the line of impact. For a perfectly elastic collision, E equals 1. For a partially inelastic collision, E is strictly between 0 and 1. For a perfectly inelastic collision, E equals 0. The physical reading of E is simple. It measures bounciness. A super bouncy rubber ball has an E very close to 1. A lump of wet clay striking the floor has an E close to 0. It sticks and does not bounce at all. We can define the coefficient of restitution cleanly using drop heights. Imagine dropping a ball from an initial height h0. It strikes the ground at speed v0. It then rebounds to a new height h1, leaving the ground at speed v1. The coefficient E equals v1 over v0. Using kinematics, this equals the square root of 2gh1 over 2gh0. The 2g terms cancel. E equals the square root of h1 over h0. If we let the ball bounce n times, e to the power of n equals the square root of hn over h0. Rearranging this, the height after n bounces, hn, equals e to the power of 2n times the initial height h0. This shows exponential decay. Each rebound loses the exact same fraction of its kinetic energy. The fraction lost is 1 minus e squared. This same factor appears in the general formula for energy loss in one-dimensional inelastic collisions. Let us analyze a perfectly elastic one-dimensional collision. The setup is simple. The velocities before and after the collision all lie along the exact same straight line. We apply our two conservation laws. First, momentum. m1 times u1 plus m2 times u2 equals m1 times v1 plus m2 times v2. Second, kinetic energy since it is elastic. 1 half m1 u1 squared plus 1 half m2 u2 squared equals 1 half m1 v1 squared plus 1 half m2 v2 squared. We can solve this system of equations. Alternatively, we can use Newton's experimental law, which states v2 minus v1 equals u1 minus u2. The results are on the slide. v1 equals a fraction. The numerator is m1 minus m2, all times u1 plus 2 times m2 times u2. The denominator is m1 plus m2. The formula for v2 is symmetric. Just swap the labels 1 and 2 everywhere. The true power of these elastic formulas comes from their limiting cases. Let us plug in some special values, assuming the target mass is initially at rest. This means u2 equals 0, first case, equal masses. m1 equals m2. The result is v1 equals 0 and v2 equals u1. The target inherits the full velocity of the incoming particle. The incoming particle stops dead, second case. A very light mass strikes a heavy one. m1 is much less than m2. The result is v1 is approximately negative u1. v2 is approximately 0. The light particle rebounds with reversed velocity. The heavy target barely moves. Think of a ping-pong ball hitting a bowling ball, third case. A heavy mass strikes a very light one. m1 is much greater than m2. The result is v1 is approximately u1. v2 is approximately 2 times u1. The heavy particle continues almost unaffected. The light particle flies forward at twice the impact speed. Think of a bowling ball hitting a ping-pong ball. These limits let you read any collision problem at a glance before writing any algebra. Memorize them. Now let us look at inelastic collisions in one dimension. The energy loss in an inelastic collision depends on the coefficient of restitution, E. The change in kinetic energy, delta K, is given by a specific formula. It equals m1 times m2 over 2 times the sum of m1 and m2. This is multiplied by the square of the relative approach velocity, u1 minus u2 squared. Finally, it is multiplied by 1 minus e squared. We can run a quick limit check. If e equals 1, the loss is 0. This matches our elastic definition. If e equals 0, the loss is maximized. In a perfectly inelastic collision, the bodies stick together. They move with a single common velocity, v. By momentum conservation, v equals m1 u1 plus m2 u2, all divided by m1 plus m2. A useful mental model is the immovable wall limit. Let m2 approach infinity. The wall absorbs all the momentum, but it absorbs zero energy in the center of mass frame. When the initial and final velocities do not lie along the same line, the collision is two-dimensional. We call this an oblique collision. Look at the diagram. Two particles approach at angles alpha 1 and alpha 2. They recoil at angles beta 1 and beta 2. To solve this, we must conserve momentum in the x and y directions separately. In the x direction, we sum the momentum components involving cosine. m1 u1 cosine alpha 1 plus m2 u2 cosine alpha 2 equals m1 v1 cosine beta 1 plus m2 v2 cosine beta 2. We do the exact same for the y direction using sine components. Be very careful with sines for the y components. A beautifully clean result emerges for equal masses. If m1 equals m2 and they approach perpendicularly, their elastic scattering will also be perpendicular. That means if alpha 1 plus alpha 2 is 90 degrees, then beta 1 plus beta 2 will also be 90 degrees. Equal mass bodies scatter at right angles. Let us look at a classic two-dimensional case, an elastic collision with a stationary target. Particle I with mass m1 moves along the x-axis at speed u. It strikes a stationary body b with mass m2. After impact, particle I recoils at angle alpha with speed v1. Particle b flies off at angle beta with speed v2. We write the momentum equations. For the x-axis, m1 times u equals m1 v1 cosine alpha plus m2 v2 cosine beta. For the y-axis, 0 equals m1 v1 sine alpha minus m2 v2 sine beta. The y equation is extremely revealing. It forces the angles alpha and beta to lie on opposite sides of the original line of motion. This is a direct consequence of momentum conservation perpendicular to the initial velocity. To solve for both speeds and both angles, you must combine these two momentum equations with the kinetic energy conservation equation. You have now walked the full arc that this chapter sets up. Let us recap the journey. Deck 1 covered work. Work is the transfer of energy. It is a force times a displacement, and the sign is decided by the angle between them. Deck 2 covered energy. Energy is the possession. It can be kinetic by virtue of motion or potential by virtue of configuration. We also saw that equilibrium is classified by the curvature of the potential energy graph. Deck 3 connected them with the theorem and power. The network equals the change in kinetic energy. Power is the rate of work, calculated as the dot product of force and velocity. Deck 4 covered collisions. This is the redistribution phase. Momentum always survives an isolated collision. Kinetic energy may not. The coefficient E parameterizes this loss. Three principles hold this entire framework together. First, energy is conserved, only changing form. Second, momentum is conserved in every isolated interaction. Third, work is the transfer mechanism between forces and energy. It is the bridge. Let us review some common traps. Trap 1, treating work as simply force times distance. This ignores the angle, always write work as F times S times cosine theta. Trap 2, assuming all forces are conservative. Friction's work grows with path length, so it is not conservative. Always check for path independence first. Trap 3, treating potential energy as an absolute value, the reference height is arbitrary. Only the change in potential energy is physically meaningful. Trap 4, thinking a kilowatt-hour is a unit of power. Multiplying power by time gives energy. Read the letter H as time. Trap 5. Comparing the coefficient of restitution along different lines of impact. E is strictly defined along the specific line of impact. Always use signed velocities along that exact line. Trap 6. Solving collision equations blindly without trying limiting cases first. This obscures the physical geometry. Always plug in equal masses, E equals 0, or E equals 1 to build intuition before doing heavy algebra. Finally, let us list the transferable takeaways. When approaching any mechanics problem, pause before reaching for F equals mi. Ask yourself if energy or momentum is conserved instead. Often, a single line of conservation algebra beats three complex equations of motion. For collisions, always identify the coefficient E first. If E equals 1, use momentum and kinetic energy conservation. If E is less than 1, use momentum and the definition of E. For equilibrium problems, read the potential energy graph. Minima are stable, maxima are unstable, and plateaus are neutral. The shape of the energy landscape gives you the answer. For power, remember it is F.V. A vehicle's engine is actually most stressed at a low speed in a high gear, where high force is required, not at its top speed. The next logical step is to rotate this entire framework. The rotational analogs of work, momentum, and inertia follow the exact same structure. We will explore those next. Please surface any unclear steps in our next session.